everyone. Alright, you had on page 129 through 130, you'll notice the second section contains that in the next page. But on page 129, 1 through 3, to define radioactive. This means that it is unstable and is thus likely to produce radiation. Alright, what does the half-life of a radioactive substance represent? This is the length of time required for 1/2 of the original substance to decay into a new substance. And the number 3, list the 3 types of nuclear decay and explain how each type changes the nucleus. So remember, there's 3 different types. So there's alpha decay, beta decay, and gamma decay. Alpha decay loses 2 protons and 2 neutrons, so 4 things total. So the atomic number decreases by 2 and the mass number by 4. We'll talk about the reasons why later. Alright, beta decay is whenever a neutron changes into a proton, so the atomic number increases by 1, but the mass number stays the same. In gamma radiation, the nucleus releases energy with no changes in composition. Alright, so let's go ahead and let's review. For your classwork, it's going to be a little bit different today. So I'm going to have you write out the periodic table, all the ones that you know, all 35. So on pages 116 to 117, write them out twice, since there's a bunch of them, but you should hopefully know what some of them are by this point, because remember, when's your quiz? Tomorrow. So make sure that you are getting ready and that you're staying on top of it. So go ahead, pause the video, write down the bold periodic table elements that you need to know and their chemical symbol just twice, but you need to know them. So go ahead and pause your video so you can work on that. Alright, if you've unpaused the video by this point, I'm assuming that you've already done it. So because of that, we're going to go over them. Now, I have all my cards, and we're going to go over them all together. You need to know for the quiz tomorrow, not just, okay, what's the symbol, what's the name, but then also, if I were to give you the name, like chlorine, what's the symbol for it? So you have to go both directions in it. So, we'll do it, this first one is like a warm-up. I'll give you the symbol and ask for the name. The next time through, I'll give you the name and ask for the symbol, and then we'll do one more kind of fast round all together, just to help get you ready for your quiz for tomorrow. Alright, AU, gold, CU, copper, NE, neon, U, uranium, KR, krypton, BA, barium, PB, lead, O, oxygen, RN, radon, RA, radium, MG, magnesium, SN, tin, AS, arsenic, ZN, zinc, W, tungsten, ZR, zirconium, P, phosphorus, Ag, silver, Ni, nickel, Na, sodium, Fe, iron, I, iodine, C, carbon, Al, aluminum, H, hydrogen, Ca, calcium, Ar, argon, Ba, boron, K, potassium, He, helium, N, nitrogen, Hg, mercury, Si, silicon, or silicon, I always heard it as silicon, S, sulfur, Cl, chlorine. Alright, let's go through them now and say, I'm going to give you the name, so that way for your quiz tomorrow, you have to do it both ways. You can't just write out, here's the chemical symbol. If you're given the chemical symbol, what's the name? So, thinking it this way, I'm going to shuffle them up a little bit. I just threw them down on my desk. I'm going to put them back in to where it's easier for me to grab. Or not. Alright, so what's the symbol for sulfur? You probably can't read it from this way because I think I wrote them too small to show up on the slide. So, what's the symbol for sulfur? S. What's the symbol for silicon? Silicon, that's how they pronounce it today. Si. What's the symbol for mercury? Hg. for neon? Sorry, neon is Ne. I looked at the wrong card. What is the symbol for nitrogen? N. I know this is probably a little bit harder, but you gotta do it both ways. What's the symbol for helium? He. What is the symbol for chlorine? Cl. What is the symbol for gold? Au. What is the symbol for potassium? K. What is the symbol for boron? B. What is the symbol for argon? Ar. What is the symbol for calcium? Yeah, I could say argon. What is the symbol for calcium? Ca. What is the symbol for hydrogen? H. What is the symbol for aluminum? Al. What is the symbol for carbon? C. What is the symbol for iodine? I. What is the symbol for iron? Fe. What is the symbol for sodium? Na. What is the symbol for nickel? Ni. What is the symbol for silver? Ag. What is the symbol for phosphorus? P. I think I held that one up too fast. What is the symbol for zirconium? Zr. What is the symbol for tungsten? W. What is the symbol for zinc? Zn. What is the symbol for arsenic? As. What is the symbol for tin? Sn. What is the symbol for magnesium? Mg. What is the symbol for radium? Ra. What is the symbol for radon? Rn. What is the symbol for oxygen? O. That is upside down for me. O. What is the symbol for lead? Eb. What's the symbol for barium? Ba. What's the symbol for krypton? Kr. What's the symbol for uranium? U. What's the symbol for neon? Ne. And what's the symbol for copper? Cu. So make sure you can go it both ways. I know going backwards is probably a little bit harder. We'll do it one more time where it's the symbols and give them the name. Because if you can do it one way, you should be able to do it the other way. After this, we'll stop and move on. Alright, so we're going to do these kind of fast. So again, if you just need to listen to it, this will help you out. Alright, S, sulfur. N, nitrogen. Cu, copper. Ne, neon. U, uranium. Kr, krypton. Ba, barium. Pb, lead. O, oxygen. Rn, radon. Ra, radium. Mg, magnesium. Sn, tin. As, arsenic. Zn, zinc. W, tungsten. Zr, zirconium. P, phosphorus. Ag, silver. Ni, nickel. Na, sodium. Fe, iron. I, iodine. C, carbon. Al, aluminum. H, hydrogen. Ca, calcium. Woo. Ar, argon. B, boron. K, potassium. Au, gold. Cl, chlorine. Ag, helium. Hg, mercury. Si, silicon. Alright, so hopefully you're studying, hopefully you're getting ready to do well on your quiz tomorrow on them. So again, you're going to take that tomorrow, so make sure that you're ready to go. So study tonight, so you're ready for it. Don't take it before you watch the video tomorrow though. We're going to review a little bit before. So make sure that you watch the video before you go and take it. Alright, let's go ahead and let's get into it. So questions, because even though you're taking your periodic table quiz tomorrow, make sure you're still going back and reviewing. What is the organized study of composition and interactions of matter? That's chemistry. Alright, what do you call a substance that's composed of a single type of atom? An element. Who proposed the atomic theory? John Dalton. There are 5 parts to his atomic theory. Name one. Alright, if you can name one, name another. If you can name 2, name another. Good job. If you can name 3 of them. So make sure you're still working on them. The 5 parts are every element consists of tiny particles called atoms. All atoms of a particular element have the same properties. Different elements have different properties because their atoms are different. Number 4, atoms of different elements can combine specific ways to form compounds. And then last, number 5, chemical processes are the results of a rearrangement, combination, or separation of atoms. Alright, what do you call just 2 atoms hooked up together? 2 or more. A molecule. What if it's 2 or more different atoms in particular? Compound. Let's see. What do you call a physical combination of elements and compounds? Mixture. What do you call a metal mixture in particular? An alloy. Alright, we talked about the chemical symbols already. Alright, thinking about the subatomic particles. What do you call the protons and neutrons together in the nucleus? It's a special term for them because they're in the nucleus. Nucleon. Which one is positive, proton or neutron? Positive is the proton. Which one? So what is the charge of the neutron? Right, it's neutral. What do we think makes up protons and neutrons? Even though we're not entirely sure. Quarks, good job. Alright, can I have the same element and have a different number of protons? No, cannot. You'll jump elements entirely. Can I have the same element and different number of neutrons? Yes, what's that called whenever I have an element that's a different number of neutrons? An isotope. Perfect. Alright, let's see. What do we call the special number that determines the identity of the element? So it's the number of protons, but we have a special term for that. What do we call it? Atomic number. Good. Alright, what do we call, what is the negative part of the atom that's flying around the nucleus? Electron. Good job. What do we call those areas where we find electrons? So those sections that hold a certain number of electrons. Electron shells or energy levels. Alright, can I have the same element but a different number of electrons? Yes. What do we call it if it's lost or gained electrons? What's the general term? An ion. What if it's gained electrons specifically? Well, positive or negative if it's gained electrons? It's going to be negative, so what's it called? Anion. What if it's lost electrons or has an overall positive charge? What do we call it? Cation specifically. Alright. So, what do we call the total number of protons and neutrons in the atom? So remember, atomic number is the number of protons. If I'm talking about protons and neutrons together, what term refers to that? Mass number. Good job. Alright, what is the unit we use to measure the weight of an atom? So, they're so small that their masses, that's a better term for it, it won't work for grams. So what unit do we use to measure them? We have to use a very small unit. Atomic mass units. Perfect for it. Let's see. Alright, I think that's as far as we got in that. So let's look over on page 120. So different types of quantum models. This is where we left off yesterday. Just made note, Dalton, he originally said the atoms were uncuttable. He thought they were these hard spheres, which is pretty close. It was a good start for it, but we realized, okay, no, they can actually be cuttable. But his was a good theory to get us started. We had another theory with Thomson's model. Didn't quite work either, though. Rutherford is the one that sticks around a lot longer. We noticed that one a lot more. So the next major one, though, as we talked about, was with the Bohr model of the atom, with the idea of you have the electrons, they are locked into specific regions. Now, make a note though of Max Planck. He came up with the quantum theory. So make a note for that. The quantum theory says that tiny particles and electrons do not absorb or release energy in a smooth flow. That you have to absorb this energy. So what he was saying that if you have them arranged like this, if you're going to have it get farther away from the nucleus, it has to have more energy. Your book describes it as a tennis ball bouncing down stairs. That's one way to look at it. You can also think of it as climbing a ladder. Whenever you're climbing a ladder, you have to keep one foot on a rung as you're climbing up. Now, you can put, whenever you put the of climbing it, typically you're going from one rung to the next rung to the next rung of the ladder. You can't hover in between the rungs of a ladder. You can't do that. Now, you can stand on one rung and then put your foot on the one underneath it, but you can't hover in between them. It's the idea of you have to be fully standing on one rung or the other as you're climbing up. So if that helps you think of it that way as well, that's fine. So, in other words, the electrons, as they change shells, they lose or gain energy. So, Niels Bohr, he took that idea with Max Planck in the quantum theory and applied it to his model. So this model is what he's showing with the idea of the Bohr model, that he's saying that, okay, that the nucleus is surrounded by the electrons and they move in these circular orbits at specific energy levels. To where, okay, these energy levels, they are locked in. And so what he's saying is, if you're going to have an electron, let's say in this one, if it wants to move out here, it has to gain energy. If it's going to go back, it has to lose energy. So that's what he's saying. So he basically took Max's Planck idea of using quantum or packets of energy to go from one energy level to another, and he applied it to a model. So that's how come his model is slightly different than Rutherford's model, is he's taking Max Planck's idea and re-updating the model. As opposed to it being like this, with all of them just flying around, he's saying no, they're locked into layers now, and you can't move from one layer to another without gaining or losing energy. So, make a note of that, that's the Bohr model. So there are several scientists you need to know by this point, so make sure you're keeping up with which scientist is which and which scientist you're working with. So, don't forget, you have John Dalton and the atomic theory, you have Max Planck and the quantum theory, you have Bohr now, Niels Bohr and his Bohr model, where he's talking about how they're locked into specific orbits, and they can only move from one to the other if they're gaining or losing energy. I said orbits by accident. Orbital is a little bit different, but they're locked into these energy layers. Alright, wave mechanical model. So, this one came about with Erwin Schrödinger. He has an awesome last name. So, Erwin Schrödinger. So, make a note for him. That he was saying with his model that the electrons, because they're so tiny, they move like a particle, but they also move in a wave-like pattern as well. And that's what this picture is trying to show you, how it's moving in a wave pattern as it goes around the nucleus. I cannot make that gesture very well because my arms and my bones will not let me do that. But it's the idea of it's moving back and forth as it's going around the nucleus. So that's what the picture is trying to show you, that it's moving in a wave pattern as it's going around. So instead of it being like Bohr's model, where they're locked into these perfect circles as they move around, that Schrödinger is saying, no, okay, they're still going around and they're locked in those energy levels, but it's not a circle, it's moving in that wave pattern as it's doing it. So, that's what he's talking about. The physicists, they have discovered in the mid-1920s that electrons have characteristics of both particles and waves. We're going to talk about this with light and photons as well, that whenever you have a very small particle, in a lot of cases, you can notice how it'll move in kind of like that wave-like pattern. Just for very, 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 very small things though. So they have characteristics of both particles, things that have matter, and waves, how they move in that particular pattern for it. So your book points out that electrons, they act like a particle whenever they act with other matter, so they can bump into another object because they have mass, so stuff can stop them. But whenever they're moving through space, they move in that wave-like pattern. Or whenever or as they travel, they are moving in that wave-like pattern for it. So that's what it's talking about. Electrons act like particles when they interact with other matter, and act like waves whenever they travel. So he was saying, okay, since you have electrons moving around the nucleus, since they're moving, they're going to move in that wave-like pattern. So Schrödinger's hypothesis, this is called the wave mechanical model, also known as the quantum mechanical model. We use this to help explain some behavior we see of the atomic structure. So not everything about the atomic structure makes sense, but this seems like a good explanation, even though you might think, that's kind of weird. Yeah, a little bit, but it makes sense for some of the puzzling aspects we see atoms do when with electrons with their very small particles. So this seems like a good explanation for it. So, wave behavior is not limited to electrons, but also occurs in protons and neutrons, but we don't focus on that as much. So, to make a note, wave mechanical model. So, this is with Erwin Schrödinger, how it moves in that wave-like pattern as it's going around the nucleus. So, make a note for that. Alright, the Heisenberg uncertainty principle is weird, but this is one of the areas of science that makes sense, but it's also also kind of a weird principle at the same time. So make a note of Werner Heisenberg that he stated that, okay, because electrons are so small, you can either know his position, where it's at, or how fast it's moving. You can't know both at the same time. You can either know its position, or you can know its momentum or speed. So make a note for this. He stated that simultaneously measuring both the position and velocity of an electron is impossible. You can know one or the other, but you can't know both at the same time. Because electrons are so small, whenever you basically hit them with a photon, that's enough to stop them right there because they're so small and so tiny. So if you hit them with light, that stops them right then and right there for us. So you can see where they're at. But because you've stopped them, you don't know how fast they're moving at that point. Now, you can also measure how fast they move. But since they're so tiny, you can't see where they're at each individual point. That's an oversimplification over what's basically happening for it. But that's the idea, just trying to say that, okay, you can't know where it's at and how fast it's moving at the same time. You can know one or the other. You can stop it and know its position, know where it's at. Or you can see how fast it's moving, but you can't see where it's moving at each individual point. Sometimes this weirds out students because they want to compare it to everyday objects. Like if I were to take a baseball and throw it across the room, or stand on one side and throw a baseball so that way you can see it. A baseball is large enough for you to track with your eyes to know where is it at as I throw it across the room. You can see it and you can tell me where is it at, where's it at each point. And you can also notice, probably have a good gauge over how fast it's moving. Since electrons are so tiny, we can't do that. Your eyes can't see it, and even photographing it with light causes it to stop. And so because of that, we can't measure and know how fast it's moving and its position at the same time. You can either know where it's at or how fast it's moving, one of the two. You can't know both at the same time. So I like this picture because it helps explain it as well. So you can either know its position or momentum. Momentum is very close to velocity. Slightly different, but it has the same idea. So you can know either its position or velocity, but you can't know both at the exact same time. So make a note for that. Your book points out that sometimes this weirds out students, and students don't like this, but why can't I know? Well, that's just part of how it is. So there are some things in science you just don't get to know. Like, why do neutrons and protons stick together in the nucleus? Because they shouldn't. We don't know. That's just how it works. So same idea. You can either know the position or the velocity. You can't know both at the exact same time. And that is something you just have to accept of. You just can't know it. Alright. So that's the Heisenberg uncertainty principle that states you either know its position or its velocity. You can't know both at the exact same time. Alright, electron clouds. So Max Born, he took the Heisenberg uncertainty principle and said, okay, if we can't know its position and its speed at the exact same time, and if they're always moving in this wave motion, we need a better model than just the Bohr model. So we need to update this for it. So he took the Heisenberg uncertainty principle and modified the wave mechanical model to make the electron cloud model. So you might look at his model and it looks just like a bunch of dots. But what he's saying is, okay, if we have the Bohr model, you're going to have the nucleus, and you're going to have the layers around it. But remember, they don't move in these perfect circles. They move in the zigzaggy patterns around it. So, because of that, he's saying, okay, the electrons are moving in this zigzag pattern, and we don't know where they're at constantly. And so because of that, I can predict a high region of probability of, okay, I probably know the electrons are somewhere in here, but I don't know for sure in this layer because they're moving in that up and down kind of zigzag pattern. For the next layer, it's the same idea. I know they're somewhere in here, but I'm not entirely sure where. So that's the idea. He's combining the Heisenberg uncertainty principle and the wave mechanical model together, saying, okay, we don't know for sure where they're at. I can either know how fast it's moving, or I can know its position. Can't know both at the same time. So because of that, if I let them move around, I know there's a high probability of finding them here. I'm just not 100% sure. So that's what his model is going off of. So it's the electron cloud model of it looks like a a bunch of dots surrounding it, so it looks like a cloud of electrons. So that's the idea behind HIB. So it represents the probability of finding an electron at a given point. They're not given definite orbits, they're given regions. So we call those regions orbitals. So electrons move unpredictably inside regions called orbitals. Each orbital can hold up to 2 electrons, and each electron shell is made up of 1 or more orbitals. I'm going to get more into this in chemistry later on, but you can have different kind of orbitals or patterns if you want to think of it that way. So your book points out each orbital in the electron cloud model can be visualized in the clouds, and that's what they're trying to show you with the shapes in this picture. So if you were to draw a circle around all of this orbital, this would look like a circle or like a sphere. For this one, it looks kind of like a dumbbell. So we call these shapes we can draw around them probability contours. So it's the idea of drawing a shape over, okay, where's the high probability of finding electrons for it? So make a note that we call these regions orbitals, and you can have 2 electrons in an orbital, but each electron shell is made up of 1 or more orbitals. So just because you have an energy shell doesn't mean it only has one type. It can have a couple different patterns or shapes. So that's what your book is showing you on the next page of quantum numbers. So go ahead and move over there. So your book points out as well that you can have a couple different shapes or patterns on the inside of it. We use quantum numbers to help describe or give the address of an electron. So the first quantum number will tell you which energy level shell that it's in. So how close or how far away to the nucleus that it is. So if you're in the first energy shell, you're given a first quantum number of 1 because you're the closest to the nucleus. The farther away you get, the higher the numbers get. Typically up to about 7. They don't get much higher than that. So the quantum numbers, this one tells you, okay, the first one, which energy level you're in. The second quantum number can describe the shape. So again, orbital shapes, so represented. So remember, they can follow all of these shapes or patterns. So it could be a sphere, that's a normal one. Or you could have a dumbbell shape, to where it looks kind of like a bow tie, or if you want to think of it as like a dumbbell, that's fine. Some of them look like clovers, so it looks like 2 dumbbells hooked up together, or it looks like a 4-leaf clover. Sometimes they have a more complicated shape, like a double-leaf clover. This is the pattern of the electrons flying around on the inside of it. So it's those probability contours. So just make a note for that the second one tells you what shape or what pattern that it's in, if you want to think of it that way. The third one tells you the orientation. Your book's trying to show you this in the picture. It's a little bit harder to see. You're going to borrow a piece of paper. So it's easier to see if you see it with an actual physical object. Sorry, piece of paper. So we'll say this represents the probability contour with a dumbbell shape. So okay, there's a couple different orientations or positions in space I can put it in. I can put it in like this, to where it's back and forth, like left and right. I can put it like this, where it's back and forth, like front and back. And then I can also angle it up and down, so it's top and bottom. So there's a couple different orientations or like angles in space I can put it in. So that's what the third quantum number is describing, of orbital orientation. It's the same shape, but I'm just holding it in space different. So that's the idea of orbital orientation. So make a note for that one. That's the third quantum number. The fourth quantum number describes the spin of electrons. Technically, that's not a fully accurate definition over what happens, because it creates the idea of if you have an electron just spinning. Technically, it's a little bit different than that, but that's a good way of thinking about it. So your book points out all the electrons are probably not hard spheres. Treating them as a spinning sphere helps us to realize, okay, which one are you talking about? So you have one electron, we say that's spinning one direction, and one that's spinning the other direction. Technically, it's not quite right, but that works for it. So those are the 4 quantum numbers. One tells you the energy level, one tells you the shape of the probability contour or the pattern that it flies in. The third one tells you the orientation in space, and the fourth one tells you which of the electrons it is in that energy level. Because remember, if you look back previously on the previous page, each orbital can only hold up to 2 electrons. So each of these shapes can only hold 2 electrons, each orbital. Now, you can have several different orbital shapes in one region of the electron shell. We'll talk more about this again as you get into chemistry. But that helps us decide, okay, which of the two electrons in this particular orbital is it? Is the electron spinning one direction, or is it the other one? So it helps us to tell the difference between them. So, to make a note of the Pauli exclusion principle, it says that no two electrons in an atom have the same 4 quantum numbers. So those 4 numbers basically give us the address of the electron. It tells us what energy level it's in, what shape or pattern it's flying around in, its orientation in space, and that will bring us down to the last 2 electrons, and then that 4th quantum number will tell us, is it the electron spinning this way or the electron spinning this direction? And so it lets scientists figure out what electron are we talking about specifically, and it allows us to give an address. Kind of like saying that you live in the United States, you live in Georgia in the United States, you live in Columbus in the United States, you live on Macon Road in the United States. You probably don't live on Macon Road for real, because that's a busy street. That's the first street I could think of. So wherever street you live at, that is your address. Or you might live in Alabama, so you live in the United States. You live in Alabama in the United States. You live in Phoenix City in Alabama in the United States. You live on Lee County Road 204, because there's a whole bunch of Lee County roads, and I do not keep track of which one is which. So I have no idea if that was even a real road, but there's a bunch of Lee roads in Alabama. So just make a note though, that's the idea behind it. We're starting on specific and get more and more specific with the quantum numbers. So the first quantum number tells you energy shell, second quantum number tells you the shape, third quantum number tells you the orientation in space, the fourth quantum number tells you which spin it is. So just make a note of the 4 quantum numbers. Alright, so Pauli exclusion principle says, like of your address, that it's saying, okay, it's more and more specific to tell where's the probability of finding this electron. And so the 4 quantum numbers let us get down specifically to one type of electron. Alright. I don't think I'm going to have enough time to introduce radioactive material, but I'll start really, really quick. So, just make a note though, changes in the nucleus. So, can you have the number of protons change and still have the same element? No, you cannot. We still have this happen though. This is one reason why you have radioactive decay, or have something like uranium decay into lead, and it changes from one whole element into another. Most of the time, the atoms, their nucleus is stable, so make a note of that. The nuclei of most atoms is stable, but the nuclei of some isotopes are unstable. They don't like being together, and they want to split apart and become stable versions of themselves. When an atomic nucleus breaks up or undergoes a change, it gives off nuclear radiation. Any substance that is unstable, we define it as radioactive. Alright, I'm going to come back and talk about it because I'm just about out of time, it looks like. So make sure you're studying the periodic table chart though, and make sure you're ready for your quiz tomorrow. Don't take it though until you start the video, because I want to review with you a little bit before. So just make sure that you wait until then. Alright, your homework for tonight. Don't need that yet. Your homework for tonight is to read pages, let me get up there. Read pages 125 through 128. So 125 through 128, answer on page 130, questions 4 through 6. It's going to be at the top of the page. So page 130, questions 4 through 6. So just make sure that it's a little bit weird how they spread it out like that. So page 130, questions 4 through 6. Don't forget periodic table quiz tomorrow. So be sure you're studying over it. Alright, you all have a good afternoon. Don't forget, hopefully the background paper will be due next Monday, so make sure you're still working on it. So hopefully y'all will be back in class by then, so the paper is due the day that y'all come back. So make sure you have it ready to go.